Glass is a non-crystalline, amorphous solid that is often transparent and has widespread practical, technological, and decorative usage in, for example, window panes, tableware, and optoelectronics. The most familiar, and historically the oldest, types of glass are silicate glasses, based on the chemical compound silica, silicon dioxide, or quartz, the primary constituent of sand. The term glass, in popular usage, is often used to refer only to this type of material, which is familiar from use as window glass and in glass bottles. Of the many silica-based glasses that exist, ordinary glazing and container glass is formed from a specific type called soda-lime glass, composed of approximately 75% silicon dioxide, silicon oxide, sodium oxide from sodium carbonate, calcium oxide, also called lime, and several minor additives. Many applications of silicate glasses derive from their optical transparency, giving rise to their primary use as window panes. Glass will transmit, reflect and refract light. These qualities can be enhanced by cutting and polishing to make optical lenses, prisms, fine glassware, and optical fibers for high-speed data transmission by light. Glass can be colored by adding metallic salts, and can also be painted and printed with vitreous enamels. These qualities have led to the extensive use of glass in the manufacture of art objects and in particular, stained glass windows. Although brittle, silicate glass is extremely durable, and many examples of glass fragments exist from early glass-making cultures. Because glass can be formed or molded into any shape, it has been traditionally used for vessels, bowls, vases, bottles, jars and drinking glasses. In its most solid forms it has also been used for paperweights, marbles, and beads. When extruded as glass fiber and matted as glass wool in a way to trap air, it becomes a thermal insulating material, and when these glass fibers are embedded into an organic polymer plastic, they are a key structural reinforcement part of the composite material fiberglass. Some objects historically were so commonly made of silicate glass that they are simply called by the name of the material, such as drinking glasses and eyeglasses. Scientifically, the term glass is often defined in a broader sense, encompassing every solid that possesses a non-crystalline, that is, amorphous structure at the atomic scale and that exhibits a glass transition when heated towards the liquid state. Porcelains and many polymer thermoplastics familiar from everyday use are glasses. These sorts of glasses can be made of quite different kinds of materials than silica, metallic alloys, ionic melts, aqueous solutions, molecular liquids, and polymers. For many applications, like glass bottles or eyewear, polymer glasses, acrylic glass, polycarbonate or polyethylene terephthalate are a lighter alternative than traditional glass. Topic: Silicate glass. Topic: Ingredients. Silicon dioxide is a common fundamental constituent of glass. In nature, vitrification of quartz occurs when lightning strikes sand, forming hollow, branching root-like structures called fulgurites. Fused quartz is a glass made from chemically pure silica. It has excellent resistance to thermal shock, being able to survive immersion in water while red hot. However, its high melting temperature 1723 degrees Celsius and viscosity make it difficult to work with. Normally, other substances are added to simplify processing. One is sodium carbonate, soda, which lowers the glass transition temperature. The soda makes the glass water soluble, which is usually undesirable, so lime calcium oxide, generally obtained from limestone, some magnesium oxide (MgO) and aluminium oxide are added to provide for a better chemical durability. The resulting glass contains about 70 to 74% silica by weight and is called a soda-lime glass. Soda-lime glasses account for about 90% of manufactured glass. Most common glass contains other ingredients to change its properties. Lead glass or flint glass is more brilliant because the increased refractive index causes noticeably more specular reflection and increased optical dispersion. Adding barium also increases the refractive index. Thorium oxide gives glass a high refractive index and low dispersion and was formerly used in producing high-quality lenses, but due to its radioactivity has been replaced by lanthanum oxide in modern eyeglasses. Iron can be incorporated into glass to absorb infrared radiation, for example in heat-absorbing filters for movie projectors, while cerium IV oxide can be used for glass that absorbs ultraviolet wavelengths. The following is a list of the more common types of silicate glasses and their ingredients, properties, and applications. Fused quartz, also called fused silica glass, vitreous silica glass, silica silicon oxide in vitreous, or glass, form i.e., its molecules are disordered and random, without crystalline structure. It has very low thermal expansion, is very hard, and resists high temperatures 1000 to 1500 degrees Celsius. It is also the most resistant against weathering caused in other glasses by alkali ions leaching out of the glass, while staining it. Fused quartz is used for high-temperature applications such as furnace tubes, lighting tubes, melting crucibles, etc. Soda-lime silica glass, window glass, silica plus sodium oxide plus lime plus magnesia MgO plus alumina aluminium oxide. Is transparent, easily formed and most suitable for window glass. See flat glass. It has a high thermal expansion and poor resistance to heat 500 to 600 degrees Celsius. It is used for windows, some low-temperature incandescent light bulbs, and tableware. Container glass is a soda-lime glass that is a slight variation on flat glass, which uses more alumina and calcium, and less sodium and magnesium, which are more water-soluble. This makes it less susceptible to water erosion. Sodium borosilicate glass, Pyrex, silica plus boron trioxide B2O3 plus soda sodium oxide plus alumina aluminium oxide. Stands heat expansion much better than window glass. Used for chemical glassware, cooking glass, car head lamps, etc. Borosilicate glasses e.g. Pyrex, Duran have as main constituents silica and boron trioxide. They have fairly low coefficients of thermal expansion 7740 Pyrex CTE is 3.25 times 10⁻⁶ per degrees Celsius as compared to about 9 times 10⁻⁶ per degrees Celsius for a typical soda-lime glass, making them more dimensionally stable. The lower coefficient of thermal expansion CTE also makes them less subject to stress caused by thermal expansion, thus less vulnerable to cracking from thermal shock. They are commonly used for reagent bottles, optical components and household cookware. Lead oxide glass, crystal glass, lead glass, silica plus lead oxide PbO plus potassium oxide K2O plus soda sodium oxide plus zinc oxide ZnO plus alumina. Because of its high density resulting in a high electron density, it has a high refractive index, making the look of glassware more brilliant, called crystal. Though of course it is a glass and not a crystal. It also has a high elasticity, making glassware ring. It is also more workable in the factory, but cannot stand heating very well. This kind of glass is also more fragile than other glasses and is easier to cut. Aluminosilicate glass, silica plus alumina plus lime plus magnesia plus barium oxide plus boric oxide B2O3. Extensively used for fiberglass, used for making glass-reinforced plastics boats, fishing rods, etc. and for halogen bulb glass. Aluminosilicate glasses are also resistant to weathering and water erosion. Germanium oxide glass, alumina plus germanium dioxide germanium oxide. Extremely clear glass, used for fiber optic waveguides in communication networks. Light loses only 5% of its intensity through 1 km of glass fiber. Another common glass ingredient is crushed alkali glass or cullet, ready for recycled glass. The recycled glass saves on raw materials and energy. Impurities in the cullet can lead to product and equipment failure. Fining agents such as sodium sulfate, sodium chloride, or antimony oxide may be added to reduce the number of air bubbles in the glass mixture. Glass batch calculation is the method by which the correct raw material mixture is determined to achieve the desired glass composition. Physical properties. Optical properties. Glass is in widespread use largely due to the production of glass compositions that are transparent to visible light. In contrast, polycrystalline materials do not generally transmit visible light. The individual crystallites may be transparent, but their facets grain boundaries reflect or scatter light, resulting in diffuse reflection. Glass does not contain the internal subdivisions associated with grain boundaries in polycrystals and hence does not scatter light in the same manner as a polycrystalline material. The surface of a glass is often smooth since during glass formation the molecules of the supercooled liquid are not forced to dispose in rigid crystal geometries and can follow surface tension, which imposes a microscopically smooth surface. These properties, which give glass its clearness, can be retained even if glass is partially light-absorbing, i.e., colored. Glass has the ability to refract, reflect, and transmit light following geometrical optics, without scattering it due to the absence of grain boundaries. It is used in the manufacture of lenses and windows. Common glass has a refraction index around 1.5. This may be modified by adding low-density materials such as boron, which lowers the index of refraction, see crown glass, or increased to as much as 1.8 with high-density materials such as classically lead oxide, see flint glass and lead glass, or in modern uses, less toxic oxides of zirconium, titanium, or barium. These high-index glasses, inaccurately known as crystal, when used in glass vessels, cause more chromatic dispersion of light, and are prized for their diamond-like optical properties. According to Fresnel equations, the reflectivity of a sheet of glass is about 4% per surface at normal incidence in air, and the transmissivity of one element two surfaces is about 90%. Glass with high germanium oxide content also finds application in optoelectronics, e.g., for light-transmitting optical fibers. Other properties. In the process of manufacture, silicate glass can be poured, formed, extruded and molded into forms ranging from flat sheets to highly intricate shapes. The finished product is brittle and will fracture, unless laminated or specially treated, but is extremely durable under most conditions. It erodes very slowly and can mostly withstand the action of water. It is mostly resistant to chemical attack, does not react with foods, and is an ideal material for the manufacture of containers for foodstuffs and most chemicals. Glass is also a fairly inert substance. Corrosion. Although glass is generally corrosion-resistant and more corrosion-resistant than other materials, it still can be corroded. The materials that make up a particular glass composition have an effect on how quickly the glass corrodes. A glass containing a high proportion of alkalis or alkali earths is less corrosion-resistant than other kinds of glasses. Glass flakes have applications as anti-corrosive coating. Strength. Glass typically has a tensile strength of 7 megapascals, 1000 psi. However, theoretically it can have a strength of 17 gigapascals, 2,500,000 psi, due to glass's strong chemical bonds. Several factors such as imperfections like scratches and bubbles and the glass's chemical composition impact the tensile strength of glass. Several processes such as toughening can increase the strength of glass. Contemporary production. Following the glass batch preparation and mixing, the raw materials are transported to the furnace. Soda-lime glass for mass production is melted in gas-fired units. Smaller-scale furnaces for specialty glasses include electric melters, pot furnaces, and day tanks. After melting, homogenization and refining, removal of bubbles, the glass is formed. Flat glass for windows and similar applications is formed by the float glass process, developed between 1953 and 1957 by Sir Alistair Pilkington and Kenneth Bickerstaff of the UK's Pilkington Brothers, who created a continuous ribbon of glass using a molten tin bath on which the molten glass flows unhindered under the influence of gravity. The top surface of the glass is subjected to nitrogen under pressure to obtain a polished finish. Container glass for common bottles and jars is formed by blowing and pressing methods. This glass is often slightly modified chemically with more alumina and calcium oxide for greater water resistance. Further glass forming techniques are summarized in the table glass forming techniques. Once the desired form is obtained, glass is usually annealed for the removal of stresses and to increase the glass's hardness and durability. Surface treatments, coatings or lamination may follow to improve the chemical durability, glass container coatings, glass container internal treatment, strength, toughened glass, bulletproof glass, windshields, or optical properties, insulated glazing, anti-reflective coating. Topic: Color. Color in glass may be obtained by addition of electrically charged ions or color centers that are homogeneously distributed, and by precipitation of finely dispersed particles such as in photochromic glasses. Ordinary soda-lime glass appears colorless to the naked eye when it is thin, although iron oxide FeO impurities of up to 0.1 Wt% produce a green tint, which can be viewed in thick pieces or with the aid of scientific instruments. Further FeO and chromium oxide Cr2O3 additions may be used for the production of green bottles. Sulfur, together with carbon and iron salts, is used to form iron polysulfides and produce amber glass ranging from yellowish to almost black. A glass melt can also acquire an amber color from a reducing combustion atmosphere. Manganese dioxide can be added in small amounts to remove the green tint given by iron oxide. Art glass and studio glass pieces are colored using closely guarded recipes that involve specific combinations of metal oxides, melting temperatures and cook times. Most colored glass used in the art market is manufactured in volume by vendors who serve this market, although there are some glassmakers with the ability to make their own color from raw materials. History of silicate glass. Naturally occurring glass, especially the volcanic glass obsidian, was used by many Stone Age societies across the globe for the production of sharp cutting tools and, due to its limited source areas, was extensively traded. But in general, archaeological evidence suggests that the first true glass was made in coastal North Syria, Mesopotamia or ancient Egypt. The earliest known glass objects, of the mid-3rd millennium BCE, were beads, perhaps initially created as accidental by-products of metal working slags or during the production of faience, a pre-glass vitreous material made by a process similar to glazing. Glass remained a luxury material, and the disasters that overtook late Bronze Age civilizations seem to have brought glass making to a halt. Indigenous development of glass technology in South Asia may have begun in 1730 BCE. In ancient China, though, glassmaking seems to have a late start, compared to ceramics and metal work. The term glass developed in the late Roman Empire. It was in the Roman glassmaking center at Trier, now in modern Germany, that the late Latin term glessum originated, probably from a Germanic word for a transparent, lustrous substance. Glass objects have been recovered across the Roman Empire in domestic, funerary, and industrial contexts. Examples of Roman glass have been found outside of the former Roman Empire in China, the Baltics, the Middle East and India. Glass was used extensively during the Middle Ages. Anglo-Saxon glass has been found across England during archaeological excavations of both settlement and cemetery sites. Glass in the Anglo-Saxon period was used in the manufacture of a range of objects including vessels, windows, beads, and was also used in jewelry. From the 10th century onwards, glass was employed in stained glass windows of churches and cathedrals, with famous examples at Chartres Cathedral and the Basilica of Saint Denis. By the 14th century, architects were designing buildings with walls of stained glass such as Sainte-Chapelle, Paris, 1203–1248 and the east end of Gloucester Cathedral. Stained glass had a major revival with Gothic Revival architecture in the 19th century. With the Renaissance, and a change in architectural style, the use of large stained glass windows became less prevalent. The use of domestic stained glass increased until most substantial houses had glass windows. These were initially small panes leaded together, but with the changes in technology, glass could be manufactured relatively cheaply in increasingly larger sheets. This led to larger window panes, and, in the 20th century, to much larger windows in ordinary domestic and commercial buildings. In the 20th century, new types of glass such as laminated glass, reinforced glass and glass bricks increased the use of glass as a building material and resulted in new applications of glass. Multi-story buildings are frequently constructed with curtain walls made almost entirely of glass. Similarly, laminated glass has been widely applied to vehicles for windscreens. Optical glass for spectacles has been used since the Middle Ages. The production of lenses has become increasingly proficient, aiding astronomers as well as having other application in medicine and science. Glass is also employed as the aperture cover in many solar energy collectors. From the 19th century, there was a revival in many ancient glass making techniques, including cameo glass, achieved for the first time since the Roman Empire and initially mostly used for pieces in a neoclassical style. The Art Nouveau movement made great use of glass, with René Lalique, Émile Gallet, and Dom of Nancy producing colored vases and similar pieces, often in cameo glass, and also using luster techniques. Louis Comfort Tiffany in America specialized in stained glass, both secular and religious, and his famous lamps. The early 20th century saw the large-scale factory production of glass art by firms such as Waterford and Lalique. From about 1960 onwards, there have been an increasing number of small studios hand-producing glass artworks, and glass artists began to class themselves as in effect sculptors working in glass, and their works as part fine arts. In the 21st century, scientists observe the properties of ancient stained glass windows, in which suspended nanoparticles prevent UV light from causing chemical reactions that change image colors, are developing photographic techniques that use similar stained glass to capture true color images of Mars for the 2019 ESA Mars rover mission. Chronology of advances in architectural glass. 1226. Broad sheet, first produced in Sussex. 1330. Crown glass, for artwork and vessels, first produced in Rouen, France. Broad sheet, also produced. Both were also supplied for export. 1500s, a method of making mirrors out of plate glass was developed by Venetian glassmakers on the island of Murano, who covered the back of the glass with a mercury tin amalgam, obtaining near perfect and undistorted reflection. 1620s. Blown plate, first produced in London. Used for mirrors and coach plates. 1678. Crown glass, first produced in London. This process dominated until the 19th century. 1843, an early form of float glass, invented by Henry Bessemer, pouring glass onto liquid tin. Expensive and not a commercial success. 1874, tempered glass is developed by François Barthélemy Alfred Royer de la Bastille (1830–1901) of Paris, France, by quenching almost molten glass in a heated bath of oil or grease. 1888, machine-rolled glass introduced, allowing patterns. 1898, wired cast glass first commercially produced by Pilkington for use where safety or security was an issue. 1959, float glass launched in UK. Invented by Sir Alistair Pilkington. Other types. New chemical glass compositions or new treatment techniques can be initially investigated in small-scale laboratory experiments. The raw materials for laboratory-scale glass melts are often different from those used in mass production because the cost factor has a low priority. In the laboratory, mostly pure chemicals are used. Care must be taken that the raw materials have not reacted with moisture or other chemicals in the environment, such as alkali or alkaline earth metal oxides and hydroxides, or boron oxide, or that the impurities are quantified loss on ignition. Evaporation losses during glass melting should be considered during the selection of the raw materials, e.g., sodium selenite may be preferred over easily evaporating selenium dioxide. Also, more readily reacting raw materials may be preferred over relatively inert ones, such as aluminium hydroxide over aluminium oxide. Usually, the melts are carried out in platinum crucibles to reduce contamination from the crucible material. Glass homogeneity is achieved by homogenizing the raw materials mixture glass batch, by stirring the melt, and by crushing and remelting the first melt. The obtained glass is usually annealed to prevent breakage during processing. To make glass from materials with poor glass-forming tendencies, novel techniques are used to increase cooling rate, or reduce crystal nucleation triggers. Examples of these techniques include aerodynamic levitation, cooling the melt whilst it floats on a gas stream, splat quenching, pressing the melt between two metal anvils, and roller quenching, pouring the melt through rollers. Topic: Fiberglass. Fiberglass, also called glass-reinforced plastic, is a composite material made up of glass fibers, also called fiberglass or glass friller, embedded in a plastic resin. It is made by melting glass and stretching the glass into fibers. These fibers are woven together into a cloth and left to set in a plastic resin. Fiberglass filaments are made through a pultrusion process in which the raw materials sand, limestone, kaolin clay, fluorspar, colemanite, dolomite and other minerals are melted in a large furnace into a liquid which is extruded through very small orifices 5 to 25 micrometers in diameter if the glass is E-glass and 9 micrometers if the glass is S-glass. Fiberglass has the properties of being lightweight and corrosion resistant. Fiberglass is also a good insulator, allowing it to be used to insulate buildings. Most fiberglasses are not alkali resistant. Fiberglass also has the property of becoming stronger as the glass ages. Network glasses. Some types of glass that do not include silica as a major constituent may have physico-chemical properties useful for their application in fiber optics and other specialized technical applications. These include fluoride glass, aluminate and aluminosilicate glass, phosphate glass, borate glass, and chalcogenide glass. There are three classes of components for oxide glass: network formers, intermediates, and modifiers. The network formers silicon, boron, germanium form a highly cross-linked network of chemical bonds. The intermediates titanium, aluminium, zirconium, beryllium, magnesium, zinc can act as both network formers and modifiers, according to the glass composition. The modifiers calcium, lead, lithium, sodium, potassium alter the network structure. They are usually present as ions, compensated by nearby non-bridging oxygen atoms, bound by one covalent bond to the glass network and holding one negative charge to compensate for the positive ion nearby. Some elements can play multiple roles, e.g. lead can act both as a network former Pb4+ replacing C4+, or as a modifier. The presence of non-bridging oxygens lowers the relative number of strong bonds in the material and disrupts the network, decreasing the viscosity of the melt and lowering the melting temperature. The alkali metal ions are small and mobile. Their presence in glass allows a degree of electrical conductivity, especially in molten state or at high temperature. Their mobility decreases the chemical resistance of the glass, allowing leaching by water and facilitating corrosion. Alkaline earth ions, with their two positive charges and requirement for two non-bridging oxygen ions to compensate for their charge, are much less mobile themselves and also hinder diffusion of other ions, especially the alkalis. The most common commercial glass types contain both alkali and alkaline earth ions, usually sodium and calcium, for easier processing and satisfying corrosion resistance. Corrosion resistance of glass can be increased by dealkalization, removal of the alkali ions from the glass surface by reaction with sulfur or fluorine compounds. Presence of alkaline metal ions has also detrimental effect to the loss tangent of the glass, and to its electrical resistance. Glass manufactured for electronics, sealing, vacuum tubes, lamps have to take this in account. Addition of lead oxide lowers melting point, lowers viscosity of the melt, and increases refractive index. Lead oxide also facilitates solubility of other metal oxides and is used in colored glass. The viscosity decrease of lead glass melt is very significant, roughly 100 times in comparison with soda glass. This allows easier removal of bubbles and working at lower temperatures, hence its frequent use as an additive in vitreous enamels and glass solders. The high ionic radius of the Pb2+ ion renders it highly immobile in the matrix and hinders the movement of other ions. Lead glasses therefore have high electrical resistance, about 2 orders of magnitude higher than soda-lime glass, 108.5 versus 106.5 cm, dC at 250 degrees Celsius. For more details, see lead glass. Addition of fluorine lowers the dielectric constant of glass. Fluorine is highly electronegative and attracts the electrons in the lattice, lowering the polarizability of the material. Such silicon dioxide fluoride is used in manufacture of integrated circuits as an insulator. High levels of fluorine doping lead to formation of volatile silicon fluoride O, and such glass is then thermally unstable. Stable layers were achieved with dielectric constant down to about 3.5 to 3.7. Amorphous metals. In the past, small batches of amorphous metals with high surface area configurations, ribbons, wires, films, etc. have been produced through the implementation of extremely rapid rates of cooling. This was initially termed splat cooling by doctoral student W. Clement at Caltech, who showed that cooling rates on the order of millions of degrees per second is sufficient to impede the formation of crystals, and the metallic atoms become locked into a glassy state. Amorphous metal wires have been produced by sputtering molten metal onto a spinning metal disc. More recently, a number of alloys have been produced in layers with thickness exceeding 1 mm. These are known as bulk metallic glasses (BMG). Liquid Metal Technologies sell a number of zirconium-based BMGs. Batches of amorphous steel have also been produced that demonstrate mechanical properties far exceeding those found in conventional steel alloys. In 2004, NIST researchers presented evidence that an isotropic non-crystalline metallic phase, dubbed Q glass, could be grown from the melt. This phase is the first phase, or primary phase, to form in the α-C system during rapid cooling. Experimental evidence indicates that this phase forms by a first-order transition. Transmission electron microscopy images show that the Q-glass nucleates from the melt as discrete particles, which grow spherically with a uniform growth rate in all directions. The diffraction pattern shows it to be an isotropic glassy phase. Yet there is a nucleation barrier, which implies an interfacial discontinuity or internal surface between the glass and the melt. Electrolytes. Electrolytes or molten salts are mixtures of different ions. In a mixture of 3 or more ionic species of dissimilar size and shape, crystallization can be so difficult that the liquid can easily be supercooled into a glass. The best studied example is Ca 0.4K0.6 NO3 1.4. Glass electrolytes in the form of Ba-doped Li glass and Ba-doped Na glass have been proposed as solutions to problems identified with organic liquid electrolytes used in modern lithium-ion battery cells. Aqueous solutions. Some aqueous solutions can be supercooled into a glassy state, for instance lithium chloride, RH2O, a solution of lithium chloride salt and water molecules in the composition range 4. Molecular liquids. A molecular liquid is composed of molecules that do not form a covalent network but interact only through weak van der Waals forces or through transient hydrogen bonds. Many molecular liquids can be supercooled into a glass. Some are excellent glass formers that normally do not crystallize. An example of this is sugar glass. Under extremes of pressure and temperature, solids may exhibit large structural and physical changes that can lead to polyamorphic phase transitions. In 2006, Italian scientists created an amorphous phase of carbon dioxide using extreme pressure. The substance was named amorphous carbonia, a CO2, and exhibits an atomic structure resembling that of silica. Polymers. Important polymer glasses include amorphous and glassy pharmaceutical compounds. These are useful because the solubility of the compound is greatly increased when it is amorphous compared to the same crystalline composition. Many emerging pharmaceuticals are practically insoluble in their crystalline forms. Colloidal glasses. Concentrated colloidal suspensions may exhibit a distinct glass transition as function of particle concentration or density. In cell biology, there is recent evidence suggesting that the cytoplasm behaves like a colloidal glass approaching the liquid glass transition. During periods of low metabolic activity, as in dormancy, the cytoplasm vitrifies and prohibits the movement to larger cytoplasmic particles while allowing the diffusion of smaller ones throughout the cell. Glass ceramics. Glass ceramic materials share many properties with both non-crystalline glass and crystalline ceramics. They are formed as a glass, and then partially crystallized by heat treatment. For example, the microstructure of whiteware ceramics frequently contains both amorphous and crystalline phases. Crystalline grains are often embedded within a non-crystalline intergranular phase of grain boundaries. When applied to whiteware ceramics, vitreous means the material has an extremely low permeability to liquids, often but not always water. When determined by a specified test regime, the term mainly refers to a mix of lithium and aluminosilicates that yields an array of materials with interesting thermomechanical properties. The most commercially important of these have the distinction of being impervious to thermal shock. Thus, glass ceramics have become extremely useful for countertop cooking. The negative thermal expansion coefficient (CTE) of the crystalline ceramic phase can be balanced with the positive CTE of the glassy phase. At a certain point, approximately 70% crystalline, the glass ceramic has a net CTE near zero. This type of glass ceramic exhibits excellent mechanical properties and can sustain repeated and quick temperature changes up to 1000 degrees Celsius. Structure. As in other amorphous solids, the atomic structure of a glass lacks the long-range periodicity observed in crystalline solids. Due to chemical bonding characteristics, glasses do possess a high degree of short-range order with respect to local atomic polyhedra. Formation from a supercooled liquid. In physics, the standard definition of a glass or vitreous solid is a solid formed by rapid melt quenching, although the term glass is often used to describe any amorphous solid that exhibits a glass transition temperature Tg. For melt quenching, if the cooling is sufficiently rapid relative to the characteristic crystallization time, then crystallization is prevented and instead the disordered atomic configuration of the supercooled liquid is frozen into the solid state at Tg. The tendency for a material to form a glass while quenched is called glass-forming ability. This ability can be predicted by the rigidity theory. Generally, a glass exists in a structurally metastable state with respect to its crystalline form, although in certain circumstances, for example in atactic polymers, there is no crystalline analog of the amorphous phase. Glass is sometimes considered to be a liquid due to its lack of a first-order phase transition, where certain thermodynamic variables such as volume, entropy and enthalpy are discontinuous through the glass transition range. The glass transition may be described as analogous to a second-order phase transition where the intensive thermodynamic variables such as the thermal expansivity and heat capacity are discontinuous. Nonetheless, the equilibrium theory of phase transformations does not entirely hold for glass, and hence the glass transition cannot be classed as one of the classical equilibrium phase transformations in solids. Glass is an amorphous solid. It exhibits an atomic structure close to that observed in the supercooled liquid phase but displays all the mechanical properties of a solid. The notion that glass flows to an appreciable extent over extended periods of time is not supported by empirical research or theoretical analysis. See viscosity of amorphous materials. Laboratory measurements of room temperature glass flow do show a motion consistent with a material viscosity on the order of 1017 to 1018 pascals s. Although the atomic structure of glass shares characteristics of the structure in a supercooled liquid, glass tends to behave as a solid below its glass transition temperature. A supercooled liquid behaves as a liquid, but it is below the freezing point of the material, and in some cases will crystallize almost instantly if a crystal is added as a core. The change in heat capacity at a glass transition and a melting transition of comparable materials are typically of the same order of magnitude, indicating that the change in active degrees of freedom is comparable as well. Both in a glass and in a crystal it is mostly only the vibrational degrees of freedom that remain active, whereas rotational and translational motion is arrested. This helps to explain why both crystalline and non-crystalline solids exhibit rigidity on most experimental timescales. Behavior of antique glass. The observation that old windows are sometimes found to be thicker at the bottom than at the top is often offered as supporting evidence for the view that glass flows over a timescale of centuries, the assumption being that the glass has exhibited the liquid property of flowing from one shape to another. This assumption is incorrect, as once solidified, glass stops flowing. The reason for the observation is that in the past, when panes of glass were commonly made by glassblowers, the technique used was to spin molten glass so as to create a round, mostly flat and even plate, the crown glass process, described above. This plate was then cut to fit a window. The pieces were not absolutely flat, the edges of the disc became a different thickness as the glass spun. When installed in a window frame, the glass would be placed with the thicker side down both for the sake of stability and to prevent water accumulating in the lead cames at the bottom of the window. Occasionally, such glass has been found installed with the thicker side at the top, left or right. Mass production of glass window panes in the early 20th century caused a similar effect. In glass factories, molten glass was poured onto a large cooling table and allowed to spread. The resulting glass is thicker at the location of the pour, located at the center of the large sheet. These sheets were cut into smaller window panes with non-uniform thickness, typically with the location of the pour centered in one of the panes, known as bull's eyes, for decorative effect. Modern glass intended for windows is produced as float glass and is very uniform in thickness. Several other points can be considered that contradict the cathedral glass flow theory. Writing in the American Journal of Physics, the materials engineer Edgar D. Zanotto states, "The predicted relaxation time for germanium oxide at room temperature is 1032 years. Hence, the relaxation period characteristic flow time of cathedral glasses would be even longer. 1032 years is many times longer than the estimated age of the universe. If medieval glass has flowed perceptibly, then ancient Roman and Egyptian objects should have flowed proportionately more. But this is not observed. Similarly, prehistoric obsidian blades should have lost their edge, this is not observed either, although obsidian may have a different viscosity from window glass. If glass flows at a rate that allows changes to be seen with the naked eye after centuries, then the effect should be noticeable in antique telescopes. Any slight deformation in the antique telescopic lenses would lead to a dramatic decrease in optical performance, a phenomenon that is not observed. Gallery. See also